Okay, we're going to go ahead and get started here. I've been waiting for this colloquium all year because it's not only it's Manuela Campanelli, who I've known since she was a postdoc actually in my group in Germany, and she's gone on to do extremely well, as you'll see. She's a professor of physics and of mathematics at the Rochester Institute of Technology, and many other accolades. I'll read her formal CV in a minute, but she's also one of the people who's been leading a group that has really not only solved Einstein's equations for the first time, and we're talking about equations that were written down a century ago and then eluded all analytical attempts to solve them for an entire century by the most brilliant mathematical physicist in the world. And then due to computational science and due to people like Manuela, they're now able to be solved by any graduate student with access to the Einstein toolkit or other simulation codes that Manuela and others have been very active in developing and so on. So I think it's like one of the major breakthroughs of computational science of the last century, and Manuela really represents that. So, and it's the field that I've spent my career not actually solving, but beating my head against the wall, trying to solve for most of my career. So anyway, Manuela's a delightful person and has been a real leader in the field. So let me just say a little bit more formally about Manuela. So she's professor of mathematics and astrophysics at the Rochester Institute of Technology, director of the Center for Computational Relativity and Gravitation. She was the recipient of a Marie Curie Fellowship in 1998. I remember that one very well. That was in Potsdam in Germany. A fellow of the American Physical Society, has received the Rochester Institute of Technology Trustee Award. She's chair of the American Physical Society Topical Group in Gravitation in 2013. And as we'll hear today, she is one of the large-scale users of the Blue Water supercomputing facility that you all know very well, and she's one of the people that's making us look really good with the kind of scientists coming out, and she's going to tell us many aspects of the science that she's able to do. So look forward to your talk.
Thank you very much for this very nice introduction, Ed. It's a real pleasure to be here among friends who I have known for such a long time and actually got me started in this field. And that's exactly when I was in Ed group at the Albert Einstein Institute years ago. Now almost 20 years ago, hard to believe, but we're here, and that's where I started to work in this field. So I'm really thankful to Ed and to everyone in his group and to the NCSA who has provided continuous resources to the work that I'm going to show to you today. So I'm going to start, and as first, I want to really give some credits to the team that I'm leading, because the work that I do cannot be done just by a single scientist. And here are just a few names. Here's as astrophysicist who I collaborate with Julian Kralik, who is a famous AGN astrophysicist. If you ever want to learn about active galactic nuclei, you can purchase his book, several of my collaborators here among faculty, postdoctoral researcher, computer scientists, and graduate students, and along with this group. Also, I must say that I must thank to the National Science Foundation for continuous support of my work and the computer resources that I had here as a PRAC here. All right, so I'm going to talk about black holes now. Okay, so first of all, there are black holes, and I don't know if you saw the movie Interstellar. They are not only there in Interstellar, so this is Gargantua that was shown in Interstellar, which was actually a realistic representation of a black hole done by a famous astrophysicist at Caltech, Kip Thorne, as you know. So there are black holes in the universe, and not just in the movie industry. So black holes are very interesting because, of course, gravity, which is the main force that governs the universe, is extremely strong close to black holes. It's so strong that light cannot even escape black hole. And so because light cannot escape, often these black holes are hidden in the universe. And the only way to detect them is either by detecting the gravitational radiation that they emit, we're going to see, which are disturbances of the space-time that happens when black holes collide with each other, or they collide with another dense compact object like a neutron star, for example. Or there is light emitted because there is gas that surrounds the black hole, and that gas moves really, really fast at speeds close to the speed of light. And so it emits a lot of radiation. Okay, so black holes are actually a solution of the Einstein's field equation, as I mentioned it. So that's the only equation I'm going to show in this talk, okay? So I don't have my intimidation slides for you today because I would need such a long, the talk would be too long for that. So that's the only equation, and that's the compact form that Einstein wrote the equations. But they are really, you know, a coupled system of partial differential equations together. And depending on whether you use a certain formulation of the Einstein's field equation or another, that number of equations can grow up to 10 to several to you know 20 or more. And then you have also, if you have matter, you have also the equations that govern how matter behave, the hydrodynamics equation. And if you have electromagnetic fields, you have the Maxwell's equation coupled together. Okay, so it's a monstrous system which I'm not going to show to you in the slides. But black holes were discovered as solutions of this theory. And if you look at, and they are the extreme property of gravity, because if you look at the strength of gravity, which can be measured by basically taking the mass of the object that you're looking to measure gravity close to, the size of the objects, and this is C, the speed of light, and G, the gravitational constant, you can see that close to the black hole, this is where the strength of gravity is the stronger. So general relativity, as Ed pointed out, will celebrate, and it's celebrating this year, particular years, because it passes 100 years of test. It's hard to believe that we got here, but it passed a numerous solar system tests, and if you have a cell phone, a smartphone, you know that this is using the GPS system, which is using the theory of general relativity. So you're using the Einstein's equation without knowing it. And you know, there's been a Nobel Prize already associated with this. There will be more Nobel Prizes as soon as we detect gravitational waves we're going to see, which is going to happen in the next few years. So it's a very exciting field. There are black holes in the universe. So how do you get black holes? So you can get black holes either because you get very large stars that are 20 times more massive than our sun. So, okay, our sun will not ever collapse into a black hole, so we'll be safe, okay? But if a star is 20 times more massive than our sun, then it can run out of fuel and then collapse in its own gravity and form a stellar mass black hole, right? An example is the famous Sinus X1 system. And then you have these very monstrous black holes that reside at centers of galaxies like our own. So these they're really massive. They may have millions to 10 billion mass times the mass of our sun, okay? And they are seen at the center of most of galaxies. So it's impressive. So how did it get there? Okay, so that's the kind of question I want to answer. So the formation of these supermassive black holes is still very, very a subject of research today, because we don't actually still understand very well how these supermassive black holes grow to this size. Okay, but what we know is the following. We know several things. So what we know is that the supermassive black hole at the center of the galaxy, like our own galaxy, is related to the velocity dispersion of the stars in the nucleus of the galaxy through this a very simple relationship, which is called the M-sigma relationship. So, and there is no particular reason why that should happen, because the stars are not really in the closed relativistic regime. So, in that sense, there is this relationship. So there is a clear relationship between the black hole and the galaxy. Black holes are linked to the birth and evolutions of galaxies in a way that we still completely don't understand. So why is that? Okay. And so we want to also know why black holes do grow to those huge, monstrous size by swallowing stars and gas, and potentially dark matter as well, and other black holes. We want to know how many of those are there by detecting them. And that's why this type of science has a lot of important consequences, not only for galactic evolution, which is important to therefore understanding the evolution of our own universe. So the thing is that black holes can come in pair. Like stars can come in pairs, black hole can come in pairs. Because we see through the evolution of the universe that galaxies do collide among them. And then it happens that their supermassive black holes should also collide and spiral eventually inward and merge in a very violent explosion that eventually will create a burst of gravitational radiation, this distortion of the space and time that release so much energy that, well, you can look at this number, it's huge, right? So, and within galaxies themselves, they can also, you can also have smaller black holes that merge using other gravitational waves, okay? So gravitational waves are, I think, the big science discovery of this century. They're going to be. We have several detectors. Some are actually operating right now, like the advanced light detector. Others at this end of the frequency spectrum, and by the way, I should explain this slide. This is the strength, let's say, of the gravitational waves versus their frequency, okay? So, and the frequency, and black holes appear all over this spectrum, okay, depending on their masses. If you're looking at black holes that are originating from the collapse of massive stars, then those, and you're looking at pair of black holes like that, then you're looking at sources that will be sources for the advanced LIGO detector that you know and the NSF has been funding, and that is actually working beautifully, and hopefully, and starting, you know, early science runs this year, and hopefully detect soon signals from this type of sources. Then if you go to supermassive black holes, then there is a space detector that was planned for many years, and now it's been pushed to 2034, and that would have detected more massive binary black holes that are in the range of 10 to the 4 to 10 to the 6 solar masses. And if you go to the end of the spectrum, you're looking at those huge monsters of 10 to the 9, you know, 10 to the 8 solar masses. And they are the sources for pulsar timing array, which is another astronomy project that is getting close to the, basically to detect this, ready for detecting this type of black holes. So you are going to see in the next few years news from here and from here, from these two ends of the spectrum. So it is therefore very critical that we are able to model these systems. And in order to do so, you have to solve the Einstein-Fields equations. Now, if you look at binary black holes in their strongest field regime, so when they get close and then and there are gravitational radiations emitted, then you can kind of split the stages of the collisions in three main portions. You have what is called the in-spiral, where the black holes are still separated enough but emitting gravitational waves, where you can treat them like point-like sources moving slower than the speed of light. And then you can use analytical approximation methods to treat this regime, okay? But when they get too close, there's no way you can use any approximation. So the Einstein's equation had to be solved numerically, fully in this regime. Okay, and that's where you go to supercomputers. And then the end is when the black holes have collided, they do form a black hole that brings down to a stationary black hole, okay? It forms just one black hole. And eventually what happens is that if gravitational radiation, which remember, those are disturbances of the space-time, okay? It's like you take a black hole, you hit it with a hammer, it will vibrate. It will make vibrate the space and time, okay? And these vibrations carry energy, an amazing amount of energy. And if this energy is emitted in a non-isotropic way, what happens is that it can impart a kick to the final black hole, and that black hole can get ejected from its own structure. Like, for example, it can be ejected from a galaxy. It can be ejected from a global cluster. So you have these rogue black holes. I don't know if you saw that in the news. Okay, so it took really a long effort. Ed was really kind to say, you know, the problem is solved, but it took a really long effort to get there. And you may recognize some faces here, some names, okay? So NCSA has, he's been here contributing to solve this problem since many years. And I won't go in details because, again, I would need to give an entire talk to review the contribution of the many, many people who have helped to solve this problem. But Larry Smart was definitely one who started the whole business in solving the Einstein's fields equation in supercomputers, so as you know well. And then there was this, then LIGO, this detector for gravitational waves that was then funded by the National Science Foundation around in the 90s, moved forwards, and then there were several projects, including a grand challenge, which involved the University of Illinois. And that's when I started. I was a grad student here, and then I came around here. You see, you recognize the name, Edward Studell here. He had a large group at the Albert Einstein Institute where we were all working together and trying to solve this problem, to take it from here to where we are today, okay? So, and around these years, you know, I must say that, you know, some people kind of always, we grew a little bit impatient after so many years, you know, and this is something interesting from Kip that I found that, you know, had lost faith on numerical relativists, but we actually did it.
He lost the bet.
He lost the bet, but he never conceived.
Right.
Anyway, so there's been a lot of effort, and now, by the way, it's not only 100 years of general relativity, but it's also 10 years of numerical relativity being solved, the problem being solved, right? So Franz Pretorius, who is now a professor at Princeton, is the one to be credited for solving this problem, okay? So, so we came after, and what we all did here was to take the formulations and the codes that Ed helped to build, and Gab here as well, and then we changed some of the gauge conditions, and suddenly things started to work. And now today we do have really, you know, codes that can do large number of orbits, so it's impressive. So today we can do a lot with that. So there are still some challenges, though, because these codes that Ed mentioned and the Einstein toolkit that Gabriel Allen has been leading arose from codes that, you know, matured to a certain stage, but they're still huge codes. If you think about it, we want to just count the number of C code, or, you know, this is not just C, but there's a large number of lines of code. Of course, you guys are not going to be impressed by this here, but it is impressive from the point of view of an astrophysicist. And so you have to solve these systems using a number of technically advanced computational tools like adaptive mesh refinement or multipatch and so on. And then if you want to solve the problem when you have also matter around a black hole, then you have to put that in, okay? So, and then there are various codes here that the community can use. Okay, let me just say a little bit more about these rogue black holes, because I think that's was an interesting discovery of numerical relativity itself. When black holes do collide, depending on whether they are spinning or not, depending on their masses, and if they are spinning, it happens that they can radiate up to 10% of the initial mass of the system into these gravitational waves, right? So that's a lot. And if this radiation happened to be in a non-isotropic way, as you can see in the movie, then the black hole can get ejected, and it will recoil to very large speeds. I put it in miles. I'm used to quote a kilometer per second usually, but it's in 5,000 kilometers per second. So the recoil it can be so large, and it can escape galaxy, right? So that was all over the magazines a few years ago, so just in case you happen to see that. Okay, so this is something new that we discovered, and I want to mention it because it's quite interesting. This is a physical review letter of a collaborator in my group. So we have discovered that when black holes have spins, an interesting phenomena can happen. I don't know, you have to follow this movie a little bit. This is not impressive for you because it's a really physicist type of movie, but you can see that the spins, after a certain number of orbits, the spins will completely reverse, okay? So I would say, what is important? It's important because, first of all, the orientation of these spins at merger is what caused these recoils to be as large as we see, okay? We compute, actually. And the other thing that is important is that if there is gas around each of these black holes, they have an accretion disk, then suddenly the accretion will go from prograde to retrograde and then prograde and so on. Okay? That will produce shocks into the gas, which produce, therefore, light that we can observe. Okay? And that's the hope here. Okay? So, so supermassive black holes can produce, therefore, very strong, also energetic emission of electromagnetic radiation, not only gravitational waves, if you have accreting gas around them. Okay, and now you can imagine when you have these monster black holes colliding with these highly relativistic gas around them, the space-time dynamics is changing rapidly, well, you will have powerful shocks and powerful light emitted from this, okay? And they will emit jets as well, which are seen thousands of light years from the source. You can imagine that? I mean, it's very powerful. Okay, so we want to look for those. And we want to understand, from looking at the light and at the gravitational waves also that are emitted, what type of system we're dealing with. So we can then, therefore, do all this beautiful science about understanding the evolution of galaxies and, therefore, understanding the role of this in the universe. So we are looking for supermassive black holes, and for that, intensive high-cadence astronomy survey would be the best. And fortunately, the NSF is funding this beautiful project here called the Large Synoptic Survey Telescope, which just started under construction. And it's interesting because when this will start, then it will be looking for a variety of sources, but not only supermassive black hole mergers, but there will be among the potential sources that they will discover. And then if you have the observation from the pulsar timing array, for example, you can combine the observations from the gravitational waves experiments to the electromagnetic observations and trying to understand, therefore, what's going on that far away in the universe, okay? And doing so, you are creating a new type of astronomy, which we now call multi-messenger astronomy, because you get messages from gravitational waves, which are an entirely completely new spectrum. They are not the electromagnetic spectrum, then the electromagnetic spectrum, and eventually, for other type of sources, also neutrinos. So this is really a new type of astronomy which encompasses all these type of observations that we're talking about. Okay, so, okay, so I'm going to have to move ahead here. I had a nice picture. But OK, so let's just say that here we need to do, therefore, accurate calculations to model what happens to the binary black holes when you have gas around it. So you start from galaxy mergers. So you have to use a little bit of imagination. I'm not sure what happens to this image here. I had tried it before it was working. But you have to use a little bit of imagination and think that you have the galaxy colliding, then the black holes get closer together. In the latest regime, you have this picture that I show it to you, okay, where there's a lot of gravitational waves emitted. And in that case, so therefore, as I explained to you before, you need to put together a complex system of equations, which involve the equation of magneto-hydrodynamics to describe what happens to the dynamics of the gas. You have to work in 3D, obviously, because that's where we live, in a four-dimensional space-time. You have to work solving the Einstein-Fields equation eventually, depending on whether you are treating this regime here, the latest regime where general relativity is important, or you are early on, you can just use Newtonian physics, but here you need general relativity. And you have to put some kind of realistic thermodynamics, okay, because you're dealing with realistic gas dynamics. You have to eventually also have some radiation feedback in order to calculate accurate spectra that comes out from these collisions, okay? So from now on, I'm going to talk to you about more recent work that I've been doing, and work that in particular I've been running here in the blue water system. But before I go there, I want to just review a little bit the status of the field so you will understand why and what I did was different from what was before. So until a few years ago, people working in accretion dynamics around the binary black holes, they were solving a complicated system of equations in 1D or 2D, okay? So by doing so, they had found that basically the binary, because of the tidal torque exerted from the binary, right, it pushed the gas away from the central region, and there was actually no gas in the central region to be heated and then emit light, okay? Today, this is no longer, we know that this picture is no longer true, but today is started only about 5 years ago, we're going to see. And this is because obviously some unrealistic assumptions were made that, the fact that you use 1D model or you use 2D model is not, you don't have the third dimension that's important, and you don't have, for example, magnetic turbulence if you don't have 3D. So magnetic fields are really important to drive accretion, okay? And also in this simulation like here, these are Newtonian point particles that are really not black holes. So you want to have a black hole with an event horizon there. You want to have a real black hole. And for that, you need to solve the Einstein-Fields equation, okay? And then you have to have also some form of describing how radiation behaves in your system. Okay, so there's been a lot of work, as I said, in the last 5 years only. And this is work that I want to cite because this has happened here at the University of Illinois, okay? And it dealt with full GR MHD simulations of the last portion of the merger. This is when the black holes are really close to each other, okay? And so they emit a lot of gravitational waves in this regime. And what they do find is an interesting double jet structure arising from these black holes. They do find, of course, strong shock heating with MHD that wasn't found before with the 1D and 2D models. And they found that the cavity that people were finding is no longer a cavity. There is gas that falls into that region. So if there is gas that falls in a very dynamical space-time region, which is moving at relativistic speeds, it's going to produce interesting physics, okay, so that we're interested in modeling, okay? So the point is that this simulation nowadays, I think not even using an entire blue water machine, for years would be feasible by using just, solving the Einstein MHD equations for many, many, many orbits. And I'm claiming that we need many, many, many orbits to solve this. Why do we need many, many orbits to solve this? Many, many orbits. The binary black holes needs to go around for many, many orbits, okay? Thousands, hundreds of orbits. Why? Because we need that the accretion disk that we put in our simulation get to something that we call the quasi-state equilibrium, okay? So, and that only happened, this inflow equilibrium only happened after so many orbits. So it is therefore critical that we are able to model this regime where you can do that many orbits, and that's the INSPIRE regime. Okay, so that's just the regime prior to merger. Do you remember that cartoon that I showed you? And because also, if you look at these papers by collaborators of mine here, they do think that they're based on some analytical estimations that some of the most interesting observational effect will come just prior to merger. Okay, so I won't go into the details here, but I'm going to speak a little bit more about the type of simulations that we're using. So we are using an MHD code. It's actually a GRMHD code, but it's an MHD code built on a dynamical spacetime. That has been also developed here at the University of Illinois by Professor Charles Gamy. And it's been adapted for a binary black hole situation. And the code is an Eulerian code, it's a high-resolution shock capturing scheme, it's in 3D, it has ideal MHD, but not only. It can take dynamical GR, as I said, and has a lot of other features. And we're going to see also has now some of the latest features about adaptive mesh refinement, as well as multi-patch and so on. I'm going to show you now some of these the movies of the simulation we run on the water, so just so you want to know what we spend for each of these simulations and how we do. So this is a simulation of a accretion disk around a binary black hole. So you see, we do hundreds of orbits in this case, okay? Thousands of orbits eventually, and to get to a regime where we can trust that our accretion disk is in this quasi-steady state inflow equilibrium that we think it should be if in a real binary this has come from, very far away, has a long time to stabilize, okay? So in a real kind of scenario. Okay, so this is the log of the density of just the log of the density. Okay, so you're going to see at the end, okay, in this movie we have, one thing that I have to say is that in this particular simulation we have excised the regions where the black holes are located, simply because to make the simulation more affordable. Okay, at the time we published this paper in 2012, we didn't have the tools that we have developed today for multi-patch, or we're going to see certain adaptive mesh refinement grade that allow us to save computational time to afford this type of simulation, even in blue water. So, but I want to speak a little bit about the science that we have found here. So we have found that the accretion rate actually is continuous, okay? There's no gap. It continues until the binary shrink to the state of close to merger, okay? At that point, the binary is spiraling so fast that the disk, the outer disk, will decouple, okay? But until then, there is really a lot of accretion. And we found that accretion happened through streams of matter. We're going to see a movie. It happens everywhere, but mostly along streams that go from the outer edge of this disk to each of the black holes. We also find a lump, which has a characteristic electromagnetic signature that we can actually eventually observe. Okay. So we have done some further studies of this, and then again, we've done this in blue water to investigate, for example, if we take our dynamical spacetime and we change it a little bit, how that influences our simulations, okay? And we have found that up to separations of the black holes are really close to the very relativistic regime, the space-time don't matter. So the space-time really matters when the binary get really very close, and that's the separation in terms of m, but this m can be translated in terms of gravitational radius. Okay, and we find also that we also have found, we have done some studies and looked at this feature, this lump that is excited, this overdensity. Because what happens is that this overdensity has an interesting signature. Because every time that this overdensity hit one of the streams that we're going to see in another movie, that goes from the outer disk to the black hole. Okay, so you have this binary. Okay, you have the streams of matter that falls into the binary, and then there is the tidal torque that push the gas out against the outer edge of the disk, which basically hit this lump of material, which tends to grow, okay? So and it depends, this characteristic lump depends on whether there is a certain mass ratio of the binary. It depends also on whether you have a larger disk, it may become weaker or stronger, okay? So this lump could be, in a way, a sensitive measure of what are the characteristics of the binary, okay? So this is still under investigation, and this was part of the subject of our first PROC on blue water. So we have been working, this is a little bit technical, this is, so I'm not going to say too much to you about this, but we have constructed now a space-time, solved the Einstein's equation, but it is analytical, okay? So that we don't have really to solve the Einstein's equation in the in-spiral regime, but we have only to solve the equation of magneto-hydrodynamics. So that was going to save computational time. But we know that we also can describe that there are black holes and spinning black holes and gravitational waves in that regime. Okay? And that's very important because, again, it allows us to save precious computational time and to deal with this in-spiral regime where you need to do hundreds of orbits. But you need to be able to resolve the black holes. And resolving the black holes is one of the main interesting, where most of the physics is happening is really close to the black holes because that's where the gas is moving at really high relativistic speeds. So in order to resolve the black holes, we have invented this, we call it the warped grid system, which is some kind of double fisheye, which concentrate, and you can see in this movie, so the grid really adapts around the black holes. It does change. The grid is actually spherical far away, where the larger disk is actually has that kind of symmetry. But closer to the black holes, it becomes Cartesian. Okay. We also have developed a multi-patch framework within the code, and now we're able to place patches around the black holes. So again, so that is also going to help to put the key resolution where we need it. So therefore, saving precious computational time, so we can run these simulations on supercomputers here. And the next thing I want to show you here is that we also have found ways now to grow the disks around each of the black holes, because what you have is not only the circumbinary disk, which encompasses the binary, but has you can see the streams here falling into each of the black holes. The streams come from the larger disk over here, and they feed into the black holes, and they form what we call these mini disks, okay? And these mini disks reach the quasi-state equilibrium faster than the larger disk. So we're able to do that, and we have found that at larger separations, where you have the analytical prediction, we can compare our results from the prediction of what is the truncation radius here of this disk to the analytical prediction, and they are in excellent agreement. Okay. So that will allow also to save potentially a lot of computational time, because to build this mini disk, so again, remember you have this very large circumbinary disk that needs to be stabilized, hundreds of orbits, okay? And then you have these streams of matter falling into each black holes, and eventually this gas accretes around each of these black holes, okay? But it takes a long, long time to do so. And so if you are actually able to put them in place, and that saves also a lot of computational time, but you have to know how to do that appropriately. So now we are ready to put things together. And so we are ready to, and this is the last simulation that we did under our previous PRAC, is a full MHD simulation that showed that in this case, we didn't have yet the mini disks I don't know why my computer is not running, probably not enough CPU. But so what happened? May I need blue wire? So I just need to get a new laptop, I think. So what you see here is gas falling into it. You see that practically there's no gap here, okay? So if you would see the movie running, actually there's no gap here. And you just start about forming the mini disk. In this case, in this simulation that we ran, before we ran out of our allocation, we didn't yet have the prescription of being able to put the mini disk in. So now we have that, and I think that's going to be the next thing that we want to do. And we want to use, of course, this Warburg grid and the multipatch to resolve each of the black holes. We want to, of course, explore the mass ratio and the spin dependence. Because remember this phenomena where this flip-flop, right? And when the spins do this complete reversal, imagine now this mini disk, right? You have this large disk, right? And then a mini disk, and then the spin flip-flop, close to merger. This is really an interesting scenario that we want to measure. And then there will be a lot of light emitted from there. So, and then we want to use post-processing tools that we have also developed to calculate the spectra, okay? So there's where we are with that. And so I just want to say something about blue water, right? Blue water has been absolutely, okay, my laptop seems to do things on its own, I'm not sure. Blue water has been absolutely critical to us, and we run on 4,000 cores. This is what we did. This is how expensive it was to do one of these simulations previously. But we think that with the new developments that we have, I think that we are going to be able to do better than this now. And so the code that we're using scales very well on thousands of cores on blue water. So for us, blue water is really an immense resource, and because just for its size and the fact that you can use this large number of cores, and also the storage and the very large allocations that one can get compared to XCs nowadays. I think it's the only way that you can do this type of science. Because, I mean, one of these simulations would just burn out just an entire exceed allocation just one of the simulation, right? So I think that Blue Water is really an absolutely wonderful resource to have. Okay, so I have a little bit of summary on the science, and then I was asked to, I know that there are some artists here, so I want to also show a project that I worked on, which is more on the outreach side. So I left it for the end. Okay, so the summary is that numerical relativity has evolved now into a really a mature field. We have predictions, gravitational waves, gravitational wave astronomy, multi-messenger astronomy is going to become a reality very, very soon. And not only that, in order to do multi-messenger astronomy, is not only unique gravitational waves, okay, which you can get by solving the equation of numerical relativity in vacuum, but you need to also to be able to model what happens to the gas around the binary, because that's the gas that emits the light, and then you want to be able to observe the light emitted from this merger. The problem is really too large to be solved by one single approach of code. So we have taken the steps, if you've seen in the talk, there were different steps that we have taken in order to get to the point where we are today. There are many scales involved, and you have to solve the MHD equation, you have to do radiation treatment, and you also have a very large parameter space, because it's not only the binary black hole parameter space, it's the mass, the spins, the orbit, okay, the separation, but it's also the accretion disk parameter space, okay, so that's very large. And so, supercomputer like Blue Water, again, it's very critical to that. And solving this problem, as I pointed out at the beginning of my talk, is really important to understand supermassive black holes, their merger rate, and their connection galactic formation. Okay, so now we're going to switch a little bit topic. I'm going to show you a video. Hopefully that's going to go.
There is a phenomena that happens called event horizon. I wanted to recreate that on the stage. So I created a short piece, it was probably 12 minutes maybe, called Event Horizon. I was so amazed at the audience's reaction, because people really were like, wow, that's cool, I've never seen that, or whatever. And it kind of got me thinking, oh, maybe we could expand this a little bit.
Thomas Warfield knocked on my door and told me, what do you think about using dance to communicate astrophysics and science to the general public and to hard of hearing and deaf underrepresented communities?
So what happens is these binary black holes will start to emit gravitational waves, and you'll get these waves that are coming out, kind of like so, and they're emitting energy. And as they're emitting energy, this distance here will actually shrink. And so these two black holes will get closer and closer and closer together. Now eventually they're going to merge. So if we can simulate how this picture works, just this basically, we can do this on a computer. We can tell all the other observers and the telescopes what we need to look for.
An interesting part was you have two different languages. Manuela and I speak the same language, the language of mathematics and science. Thomas speaks the language of art. And in order to get these two languages together, one of us had to learn the other ones. And at the end of the day, both people understood what the other one meant.
And so in a way, I think it really had to do with both dance and science really equally, even though science had the content, dance was the vehicle, but they both sort of, you could see science in a different way and you could see dance in a different way.
This is a small observatory we have there. This is the president of our university. Okay, so I would just want to say a few more words here about this project. This was funded by the National Science Foundation, and the artist who speaks at the beginning of this video is Thomas Warfield, who is a well-known, he was well-known in his field and has done previous work with Carl Sagan. And one day, as he said, he popped in my office and told me, you know, what do you think about using your science together with my dance? And, you know, and so we brainstormed a bit, and that's how this happened. And it's been an interesting experience overall, and so I just want to show that. And thank you very much for listening.
How expensive is the post-processing, the ray tracing or the radiative transfer?
Tracing? Well, it depends, right? But I don't think I think it's a fraction. It's just a fraction of what we spend in the simulation. It's not really so much expensive. And you know, it scaled tremendously well. When we use a different code, the code is called Bartos, and we use a different code than this. So it's probably a tenth of what we spend for the simulation. Okay.
During a lot of our tours that we do of blue waters, we get a lot of questions about what runs on blue waters, and you know, we use a lot of astrophysics examples. So recently we've had Interstellar's brought up a lot of questions. So what can we say to people about black holes that we could tell, like within a quick sentence or two, to someone during a tour, elementary school students, or something that would be useful? So there was one comment, I think it was made recently, that there's like a black hole inside every galaxy.
Yes.
Something like that. So are there something that you could tell us, or that would be useful for relaying that kind of information from blue waters to the community?
Yes, I think black holes are, first of all, very fascinating objects, not only for astrophysicists, but for the general audience. So if you want to pick a subject, that's definitely a subject a lot of people are interested in, and that's why we did the Astro-dance project. So the supermassive black holes at the center of our own galaxy is definitely, something that attracts a lot of people. It's here. We know that it's there. We see the stars moving around that at relativistic speeds. So mentioning this huge monster at the centers of galaxies, and that it happens, all over the universe, that all galaxies have these huge black holes at their centers, and when they do collide, they emit such a powerful gravitational waves, and that basically the luminosity of this thing outshines the entire universe for very few moments. Okay, and if you want to talk then about the physics of the black holes, it's very interesting to talk about that too, because obviously a black hole is a very strange object, although it's a very simple object in terms of its physical description, because it only depends on its mass and its spin. But the fact that, like you see in Interstellar, everything that goes down to a black hole never comes out. It's something that's basically accurate, you can say, depending on the level of the audience that you're dealing with.
Although in Interstellar, miraculously, He gets out.
Yes, well, I'm not going to say this because it's going to stay recorded in YouTube, but yeah.
By the way, just on that, Interstellar, if you haven't seen it, at least a lot of it, if you work in relativity, you probably either love it or you hate it. Actually, Bill Press told me he hated the movie. Actually, Bill was one of Kip's students. But anyway, there's a book called The Science of Interstellar that Kip wrote, where every single scene he goes through the detailed physics of it, but at a level that's supposed to be accessible to a bright high school kid. So, although I've spent my whole career in general relativity, there are parts that I've really struggled through trying to read that, and I don't understand them.
Oh, that's right. And the things that you saw also in Interstellar, now I remember that time slow down, close a black hole. You can use that, the twin paradox, that you also see, as if you remain on Earth, your time runs differently than when you go close to a black hole, right? So your time slow down. So if you go back and you will meet your twin again, you're going to be younger, right? So these things, I think, is something that fascinates the public.
And so maybe this sort of follows on to the previous question. So one of there's so much going on in relativity. Another thing that is exciting about black holes is the fact that we are on the verge this year of having gravity wave observatories, as Manuela told us, that will for the first time see the mergers of neutron stars and black holes merging, and we'll see the birth of a brand new black hole, either from the merger of two or from two neutron stars. And the gravity wave signals from those that we'll directly measure, that's what Manuela is burning all of her Blue Water's time to learn about. And so what I was wondering, I probably should know this, but I don't. How difficult is it? So when the signals from LIGO, some will be from neutron star mergers, some will be from neutron star black hole, and some will be from binary black holes. From the gravity wave signal alone, how difficult is it to tell which of those situations we have?
Okay, so this is a question that, so with confidently, I think we can say that we'll be able to distinguish the masses of the black hole pretty well, depending on whether you're looking at which detector, okay? So you're looking at advanced LIGO in the next few years. We're going to probably be able to say, whether we have a neutron star binary system, whether we have a black hole system, what will be their masses, okay? Whether we're going to be able to, in their first measurement, to say which spins they're going to have, that's going to probably have to wait a few years more, and has probably to wait the era of multi-messenger astronomy to get there. And the other thing that we're going to learn, I think, relatively quickly is the rates. How many of these types of sources are there? Because those already tells a lot, okay, about what's going on in our universe. Because most of these sources, and as in my title, revealing the hidden side of the universe, most of these sources are invisible. So the supermassive black holes, you can see them because they have gas around it. They have accretion disk. Okay, but in the case of smaller black holes and binary black holes, smaller black holes, it's very unlikely that an accretion disk survive because there's no feeding mechanism. Okay, so in that case, the only way is really gravitational waves. And so knowing how many of these sources is important to know.
I think we're out of time, but I know Donna had a question. Is it just a quick?
It's been even within my lifetime that we've discovered so many galaxies in the universe. And to make a statement that every one of these galaxies has a black hole, when did scientists start to agree upon this theory? And was it primarily computational science or observational science or the combination of both that brought about that agreement?
You're bringing up an interesting history question here. So black holes were first a mathematical fiction, okay? So not even Einstein believed that these were really physical objects at that time. And really it wasn't until the Oppenheimer collapse that, black holes became associated with physics, that they can arise from the death of stars. So when stars collapse, So the star run out of their fuel, and then they can form black holes. And at that point, black holes, and now we're around the 60s. Okay, so at that time, so then they became associated more with physics. Then the first radio observations showed, we discovered, quasars, this very large structure. We started to look at the centers of galaxies, and we started to see, this highly relativistic gas moving, in the central regions, and that observations were in agreement with what, the theory of Einstein relativity would have predicted for how fast, this gas and what kind of electromagnetic radiation it would meet, close to. So a lot of mass concentrated in a small space. Okay, that's the thing. And if you believe that Einstein general relativity is the right theory to describe gravity in strong field regime, okay, which is something we still have up to prove directly, but we know indirectly already because there is a Nobel Prize associated with the binary pulsars. But anyway, so because of that, then the astrophysics community started to look at centers of galaxy. They saw more and more sources like that. And so it became widely accepted already in the 80s, that black holes were residing as centers of galaxies, okay? So then there's been a shift in culture, and then in the early 2000s, you have this M sigma relationship discovery. Okay, there was even an early paper in the 70s that discovered that relationship. But it showed, you remember that relationship that I showed at the beginning of my talk? It shows that the masses of the supermassive black holes are linked to how the stars moves around, not in the close of the black holes, but in the galaxy, okay? And there's no apparent reason why that should be. And so, we still don't understand why that relationship exists, but clearly it indicates, and it's been tested. It's been observation. You've seen that relationship. You have many galaxies along that, and so it is clear that the black hole is linked to the evolutions and the birth of the galaxy. We still really not understand how black holes grew to this size. We do think that is a combined accretion from the gas, okay? And then also the fact that black holes have collided among themselves, because we do see galaxies colliding among themselves, okay? So that's the short story of it. And that M sigma relationship also changed a little bit the view, because now we know that there are black holes at the centers of galaxy, and we're trying now to understand why and how they grew. Okay, so that's now the most important question. That's a fact. We are trying to understand that. And the other thing is that there is an interesting project I hadn't had time to mention here. It's called the Einstein telescope. It's trying to image the black holes at our own centers, the galaxy. And I know Charles Gamming here is involved in this. So it's really amazing. So you can see at the stars close to our black hole in the Milky Way, really moving at the relativistic speeds we expect to be, and and the orbits that we expect to be if there is a supermassive black hole there. So it's really amazing, and now they want to really image the event horizon of the black hole.
Okay, thank you so much, Manuel. It's been a great talk. Thank you.